Our speaker today is Zi-xia Song, and she'll speak on minimum numbers of edges in H1 to HK co-critical graphs. Zi-xia, the floor is yours. Thank you.
Thank you. Yeah. Now, first, I want to thank Sandra for giving me the opportunity to speak at New York Combinatorics Seminar. And I also want to thank everyone for coming today. So I will talk about the topic that I am getting interested on H1 through HK co-critical graphs, because I know Sandra also works with undergraduate students. That's why this is based on joint work with 3 of my undergraduate students, Ivan, Hunter, Benjamin, and 2 of my PhD students. And these are the visitors from China, okay, from China. So let me get started here. It's more like a survey talk because I find that this topic, also the motivation is to sell this topic. Hopefully some of you may get interested after my talk, okay? And let's get started here. So this is, to be on the same page, let me start with the basic one here. So we use bracket K to denote the set of first K integers. Normally this K represent the K colors, okay? We just denote my color set. Now given graphs G and H, so a K coloring of the edges is simply a function. Okay, it's simply a function from the edge set to K. Now, once again, as I said, this normally denotes a set of K colors. Well, my coloring is not necessarily a proper edge coloring. And what do we mean by monochromatic copy of H contained in G and then the coloring tau? It means you can find a subgraph in G here, let's call it H prime, isomorphic to H, but all the edges of H prime are colored by the same color. So this means monochromatic. So I think everybody knows this arrow notation. We say G arrows H1 through HK if every K coloring of the edges of G contains a monochromatic HI for some color I. So we all know K6 arrows K3, K3. So I won't give you a proof here now. And the classical Ramsey number says is defined to be the smallest integer n, such that Kn arrows H1 through Hk. When these His are all the same, we use this shorthand to denote, and this is the Ramsey number. And we all know Ramsey number exists, for any given H1 through Hk. So that's the one. So what do we mean by G does not arrow H1 through HK? So it means you must be able to find a 1K coloring, right? Such that you cannot find any monochromatic HI. For every color I, you cannot find the corresponding one we are looking for. Now, such a coloring is called a critical K coloring of G. Sometimes I just call it a critical coloring when K is 2. Now, for example, for K5, we knew K5 does not arrow K3, K3. Here, this is the unique critical coloring of K5. Now, this is the drawing of C5, C5. So you take 2 copies of C5, you add all possible edges between them. This defines the drawing here. Now, this C5 cross C5 does not arrow K3, K3. I give you a critical coloring here. That's the one critical coloring I provided for you here. So now the question we want to study here is the following. So I give you a non-complete graph. So we need this non-complete here because I don't want to deal with the small complete graphs. The complete graphs whose order has few number of vertices. So I don't want to have these trivial cases there. So H1 through HK is given. Okay, we say G is H1 through HK co-critical if G does not arrow H1 through HK. However, if you keep adding any edge in the complement of G and add it to your graph G, now the arrow notation holds now. So this one holds. So if you, many of you may have read it in this way, a graph G here does arrow this one. If you deleting any edge from G, then this arrow notation no longer holds. That's called a Ramsey minimum. This is the opposite of that definition here. Now for this one, if G is H1 through HK co-critical, now one thing we can tell is the number of vertices in G has to be at least the Ramsey number, right? Has to be the Ramsey number. And the G itself has a critical K coloring, but if you're adding any missing edge to G, it's you no longer have one. So this is the basic definition here. Now, who introduced this definition? Now, before we get started here, let me show you an example here. I use this one to denote a graph obtained from the complete graph by deleting an edge. Now, this is a K6 with one edge removed. And you see here, I give you a critical coloring of K6 with one edge removed graph here. This graph is K3 co-critical because the graph G itself has a critical coloring. I showed you here. This actually is going to be the unique one. Now, I only have one missing edge. If I add this missing edge, I obtain a K6, right? And we knew K6 arrows K3. So this graph is K3 co-critical. Now, this definition here actually was initiated by Nestria back in 1986. And he was asking here if there are an infinite number of minimum co-critical. His co-critical means K3 co-critical graphs. Now he's not sure if K6 with one edge removed is the only one. Now to the first question here, Galuccia, Simonovich, and Simoi here, they answered this question in the positive. Means you can have infinite many minimum co-critical graph, K3 co-critical graphs. Now to state their construction for you, I need one more definition here. What do we mean by F-saturated graph? Now this topic was extensively studied, I think, back in the 80s or 70s and 80s. Many researchers are done on saturated graphs. So the definition I give to you for co-critical graph reminds you of saturations, right? So what do we mean by a graph G is F-saturated? It means G does not contain F as a subgraph. But if you add any missing edge to my graph G, it will contain a copy of F. Now, for example, C5 doesn't have a triangle, but if you add any missing edge, you will have a triangle. So C5 is K3 saturated. And when we started working here with my former PhD student, Martin Rolik, we, for K3, we are looking for non-biptide K3 saturated graphs. And with minimum degree 2, and your graph is isomorphic to this one. So this is an independent set, independent set, independent set. This is a completely adjacency here. So we have infinite many here, K3 saturated graphs that are not biptide. Now, so for this one here, now their construction, if you take any two non-biptide K3 saturated graph, and you do join in this way, you can prove such a graph is K3 co-critical. So you can construct many you like. And they provide many constructions. I only list two here. Another one, they use method graph. And let me not define this one here for this one. So for their construction here, the maximum degree of all these constructions is very big. It's linear in terms of number of vertices. Okay, so they were asked here, is it possible you can construct one whose maximum degree is not a linear copy of the number of vertices you have? And this was answered by Zebel back in '96. And he can construct one, the maximum degree is big O of number of vertices to the 3/4 here. So this was, but we don't know if one can lower the maximum degree here. So I didn't work along this area. But what we wanted to study here is the number of edges in co-critical graphs. So of course, the first one would be similar to Turing's problem. You would like to ask a maximum number of possible edges. This turns out to be trivial. It's exactly Turing's problem. So this can be solved quickly. And these two different groups, one is by Hans and Toft, and this is Zi-xia Song and Simui here for this one. And we would like to see the minimum number of edges for this one. Now, this was first studied by Hans and Toft in 1987. Now, these two groups are working on the same thing, but they don't know they actually didn't know they are working on the same thing because they were studied under different names. So let me tell you why. So that's why this was first studied by Hans and Toft in 1987 under this name. And they studied it in the co-critical definition. So for Zi-xia, they studied in the co-critical one. Now, also recently here, this topic has been also studied under the name of Ramsey minimum. This stands for Ramsey minimum saturated graphs. Now, let me give you the definition here. Now, we say a graph G is H1 through HK Ramsey minimum. If G itself arrows H1 to HK, but if you're deleting any edge from a graph, this is no longer true. Now, from this point of view, we see K6 is a K3 Ramsey minimum. Now, and also if G arrows H1 through HK, then you must be able to find a spanning subgraph of G, which is a Ramsey minimum. Just keep on removing edges, right, until it's Ramsey minimum. So you can do that. And if you put all these Ramsey minimum graph together into a set, so this is the definition here. Now this family of graphs is very well studied. I mean, not very well studied. I meant a lot of questions have been studied on this family of graphs. The first parameter would be the Ramsey number, right? You are looking for the graphs in this family with minimum number of vertices. So you see my notation is slightly, I define it here. So the minimum number of vertices is defined to be the Ramsey number. And we also have size Ramsey number, study the minimum number of edges in this family, right? In this family. So now you look at the definition of saturations. Now, if my graph G is this saturated, arming saturated, if no member in this family here is a subgraph of G, but if you put any missing edge to my graph, it will contain some member in the family. Some member in the family. Now, if you think it, so this part of the reason I think not many people are working on this topic, because this definition can confuse students a lot in a sense. So if you think, take a moment to think about this definition here, you will see if my graph G is arming saturated, if and only if G does not arrow H1 through HK, but if you add any missing edge to my graph, it will arrow H1 through HK. So now because of this, now I think starting a couple of years ago, I stopped using Ramsey minimum. When I first studied this topic, I read the paper on Ramsey minimum saturation paper. Later on, I stopped using it. I think because the definition of a co-critical here is much clearer. It's much clearer. So I will just stick to co-critical graph definitions. Okay, co-critical graph definition. Now, another one here, we try to study the minimum number of edges of co-critical graphs. Now, a natural question would be, let's start with complete ones, when each HI is a complete graph. Now, can you construct the one with linear bound of edges? Linear bound of edges. Now, we know KR arrows, I is the Ramsey number. But if you deleting any vertex, this is no longer true by the definition of Ramsey number, right? So now let's see for K3 co-critical graphs gives you a construction here. How do I construct for each n you give me, I'm going to construct a K3 co-critical graph for you with a linear bond of edges. Now we start with n equals 5. We know this one has a unique critical coloring, 2 coloring here. Now for any n at least 5 you gave me, I'm going to do the following. Now first I'm going to redraw my K5. I single a vertex out, now together with all the coloring here, okay? Now for any n you gave me here, I'm going to duplicate this vertex. A minus 6 times, A minus 5 times, A minus 6 times here in this sense. Now I'm going to duplicate. When I duplicate, I also duplicate the colors the same. Okay, so this becomes K4 join the complement of K minus 4 or independent set on A minus 4 vertices. So I need to duplicate A minus 5 times here. Now this graph, now from this picture, you see I created a co-critical coloring for you, right? And this graph doesn't have red K3, doesn't have blue K3. But if you're adding any missing edge here, you get a K6. Now this construction gives you 4A minus 10 edges. So I do it slow. I thought I may have undergraduate students here. Sorry if you are bored during the talk. Now, what about the general case? You do the same. Now, the same idea can be generalized, right? You single a vertex and together with the colors, and you just duplicate it the number of times you are looking for. And this construction is due to Hansen and Toft in the paper published in Journal of Graph Theory. And this graph has exactly this many number of edges. It's a linear bond here. It's R minus 2 times n. It's a linear bond of edges here. So they made a conjecture here. Now look, so I want you make an observation here as well for this graph. Its minimum degree, is R minus 2. Its minimum degree is R minus 2. So they made the following conjecture. They believe the construction they had is the lower bound here, and this bound. If this is true, every such co-critical graph must have at least this many number of edges. Now, if this is true, then this if this conjecture is true, then this is the best possible for all n at least R from the previous construction here. So you see, from 87 to 2011, there is no progress on this conjecture at all. Or I don't know if no one found this conjecture or no one was interested in this conjecture. That part I don't know. So the first progress came in 2011. So this group of people here, they solved the first non-trivial case. Now for n at least 56. And by far, this is the only solved case for this conjecture. Now I spent some time for K3, K4. I still don't have a proof for K3, K4. So by the end of my talk, I won't pose any open problems because there are so many during the talk, okay, for this one. So only one case is solved. So I got interested on this topic because Michael Ferrara visited me in fall 2016. Now, before he came, I tried to look for some topics we can work on together. But he was very busy with his huge education grant. So I got interested when I reading this paper. So I tried to see if we can do something. And now before he came here, there was also a paper. Michael Ferrara continued this work, and this was a GRWC project. So they, with two graduate students, they did the multicolor version. So you don't have, HI do not need to be a complete graph. For any general case, can you determine the minimum number of edges of these co-critical graphs? Now they also studied the same thing in their paper for two colors when this one is a P3, So for multicolors here, now this is the, if each HI is a matching, they solved this problem, okay? So this is the very first result on multicolors. And their strategy is quite nice, but only works for matching, So what we continued here is, this is a K2, what if it's a K3? Now I was surprised that they didn't try K3 first. So actually P3 actually is much more interesting in the sense if you knew H coloring. Okay, if you knew critical, the other critical graphs or within the adjacency lemma. Okay, so we did a multicolors when each one is a P3. However, if you change a P3 to two copies of P3, then our method is no longer working. Okay, so this one is I find it's more interesting because if you look at if my graph G is P3K co-critical, what does it mean? It means if you take a critical coloring of your graph G, such a critical coloring must be a proper edge coloring of my graph G, because I cannot see monochromatic P3, which means any two adjacent edges must receive different colors, right? Because I don't have a monochromatic P3. So my P3 here is a path on 3 vertices. So this monochromatic is forbidden. So which means any two adjacent edges, they must receive different colors. They must receive, so it's a proper edge coloring. Now, if you add any missing edge to my graph G, my graph is no longer proper K edge colorable now. So this has something to do with the adjacency lemma. We actually prove a stronger result. But our bound here is not no, it's n has to be at least 3 delta over 2 here for this one. That's for P3. So I did a multicolor first because it's now we only have 2 results here. Now I'm going to come back to 2 colors. So this is the one when Michael Ferrara visited me. I asked him, I mean, you did a K3 P3. Let's see if we can do K3 P4 or K3 a claw here, right? Just to do some homework. Originally, I thought that this would be trivial, but for the afternoon discussion, I couldn't solve it. So what I did is I added these 2 together. But I didn't read their paper in entire. I didn't read it there. I only read the first part. So only after I finished last year I noticed that they actually had a conjecture in their paper, and this conjecture actually is very wrong. It is very wrong for this one, and you're going to see in a little bit. Okay, for this one. So what I did is I put all trees together. So I use TK to denote the formula of all trees on K vertices. Now you can define the same thing, the arrow notation here. G arrows, the first one is one graph, the second one is a formula of graph. I only need one of them to be there, okay, to be there. And you can define KT, TK co-critical here. So I want to determine this one. I thought if I put all trees together, it should be trivial because I only need one tree on K vertices. The answer actually turns out to be not trivial at all. So, when Michael Ferrara left, I already have a proof for K3 T4. So then I told my student Martin, I said, if you construct a graph for me here, and your name is on the paper. So that's how we try the K3 T4. When I put all trees on 4 vertices together, that's just the P4 and the claw there. You don't have many. Put it together, you have this one. And with my PhD student, Jin Mei Zhang, we were able to prove this one for any TK. I will mention a little bit later our proof strategy here. And the proof is quite involved. Now, unfortunately, we were unable to prove this is asymptotically best possible for all t. We can only do for up to 5 here. For t equals for K6 TK, we were unable to construct such a co-critical graph with this term correct the number of edges there. And to construct, to show the sharpness of this result, it actually is quite non-trivial, Now let me see here. So majority of our efforts here have been devoted to proving the sharpness. How do you construct such a co-critical graph? You need to construct a graph which has a critical coloring. But if you're adding any missing edge, this is no longer, it does the error, right? It no longer has a critical coloring. Now you can imagine how much work is going to be there if you construct the graph with many critical colorings. So our strategy here is always, I try to construct one with a unique critical coloring. Then it's trivial for you to adding an edge, color it red, you see a red triangle. Color it blue, you see a blue triangle, let's say. So this is our strategy. Before 2022, my strategy is to construct one with a unique critical coloring, okay? And I want to show you how we prove such a graph is co-critical. At least you see the critical coloring. The coloring I showed you is a critical coloring. The trouble is to convince me you have a unique critical coloring up to symmetry. I meant up to symmetry, okay? So that's for K3, and this is for K4. And when you see K5, and you understand why we stopped the constructing for K6, because I believe this construction won't work for all KT here. I need so maybe someone else can come up with a simpler construction, That's for trees. Then after I'm done with this one, I think a colonel is very doable. So I assigned it to my undergraduate student. Okay, so he did his honors thesis on KT K13 on KT K13. So he proved this one. He can prove every K3 K13 co-critical graph has at least 3a minus 4 edges. This is bigger than K3P4 or K3T4, and this is best possible. So then with a PhD student from Shandong University, now we were able to complete for any star here, but still for the sharpness, we can only do this because the construction comes from my TK construction, KT TK construction. For that one, we can only solve for T up to 5, complete the graph up to 5 vertices. So that's why we also stopped here. We don't know how to construct the next case. So this one. The stars actually turns out to be much easier, slightly in terms of counting edges is much easier than our TK. Okay, TK. So that's for stars. Now I also want to find everything for path. If the first one is a complete graph, I want to do path. Path turns out to be the most challenging one here for this one here. Our lower and upper bound, there is a big gap between them. I cannot make them agree. But for P4, we did solve for P4 now. All the we can solve this one because of the K3 saturated graph we found with minimum degree 2. I was surprised that characterization was open when I came to work on in this area. I didn't show you any proof strategy yet. I will tell you in a little bit. Okay, in a little bit. So now, recently here, this year with my visitor, Gang Chen, and his master student, Ren Chen here. So we try to see here, we want to see, can you do, you would like to do cycles, right? It's like a K3 is no, what about the C3 is no, what about the C4? What about the C4 here? C4 star. And we were able to determine the minimum number of edges in C4 star co-critical graphs. The proof actually is quite cute. I really like it. And if this is a P3, we find the sharper bonds. We find the sharper bonds. And we didn't try to determine K13 because even for the because we already have this asymptotic bond here, asymptotic bond here. Now, these are the minimum number of edges. Now, on co-critical graphs, you like a size Ramsey number. Now, people also study the minimum degree in Ramsey minimum graph or Ramsey minimum graphs. Now, you can do the same. You can do the same. So in the same paper, they proved that every K3 co-critical graphs has a minimum degree at least 4. And from the construction I showed you, now this result is best possible for any n at least 6, right? For any n at least 6. So this is remember I showed we have construction kr minus 2 join with the completed graph on a minus r plus 2, the complement here. The minimum degree is r minus 2. R is the Ramsey number. So this one. Now, just now, this summer with my undergraduate students, Casas Rocha and Schneider here, we can extend this one to K3, K4. We actually did more. We should be able to put our paper on archive next week. So we have more. So we can prove the next one. Now, we didn't try K3, K5. We didn't try K3, K5. We would like to see if there is a, to generalize. So there is a study of minimum degree here for co-critical graphs, okay, for co-critical graphs, as it was studied for Ramsey minimum graphs. Now let me, for the remaining time, let me tell you what are our proof strategy here. Why do I saturated F-saturated graphs? Now to prove the minimum degree, we need to use an observation made in their paper. So I put it as a lemma. I'm going to provide a proof later on because this lemma is only true for when each HI is a complete graph. Okay, you actually can say something about its chromatic number. The chromatic number of any co-critical graph here is at least its Ramsey number minus 1 if each HI is a complete graph. Now, for example, if my graph H is a star, if my H is a star here, you take a complete bitype graph. And this has chromatic number 2, and the Ramsey number is 2t minus 1, can be far away from each other. Okay, can be far away from each other for non-complete graphs. Okay, for non-complete graphs. So these will be used to study the minimum degree for this one. Now let me tell you here, how do we find the edges in co-critical graphs? So I will just focus on 2 colors. This is the strategy I used, not the one used in Michael Ferrara's paper. So this is how I can solve the minimum number of edges for KTTK co-critical graphs. Okay, what I did is the following. Now let's say I take a H1, H2 co-critical graphs. Okay, I know it has a critical coloring. Now among all critical colorings, I'm going to pick one out so that the first color, let's say first color is red, second color blue. I have maximum number of red edges. Maximum number of red edges. Now ER denotes the number of red edges, EB denotes the color classes here. And these are the spanning graph. I call it a red graph and a blue graph. Blue graph is a spanning graph of G with all edges colored blue. Now this one, all edges colored red in my graph G. Now to find the edges in G, all I need is to find the red edges, find the blue edges, then add up, right? Then add up. So I just need to estimate red edges and the blue edges. Now, why do I choose my red edges to be maximum? So if I pick it to be maximum, now you look at my red graph GR, it has to be H1 free because it doesn't have a red H1. Now, if you pick any edge not in my red graph, So this edge could have colored blue, right? If it's colored blue, now I cannot color it red because I choose my red edges to be maximum, right? If I recolor such a blue edge to red, I must have a red H1. Now, if this edge E is not colored blue, it's not in my graph G at all, it means it's a missing edge of G. Now, because my graph G is co-critical, adding any missing edge, it no longer has any critical coloring, right? So with this choice here, now you know my red graph is simply H1 saturated. H1 saturated. But as I mentioned earlier, saturations of the number of edges in the minimum number of edges in F saturated graphs were very well studied in the last century, and a lot of research there. In particular, when F is a complete graph. When F is a complete graph. Now this was for KT saturated graph. It was first studied by Eldish, Heiner, and Moon back in 1964. Then Tufts and Hansen here prove for K3 saturated graph, if minimum degree is 2, they give you the minimum number of edges. They didn't give you the structure. So our result, I need a structure in order to study K3 TK co-critical graphs. I have to know the structure, otherwise I don't know how to construct to prove the sharpness. So they did provide edges, but no structure. Minimum degree, they did this one. And for K4 saturated graph, along Eldish, Hosmer, and Krivilic here, they did for minimum degree 4 case. But I tried to do minimum degree 5, it turns out very non-trivial. I still don't have so we cannot solve K3, K4 because I don't know the number of edges and the structure there for this one. Now, what really useful one to us is a result due to Heiner. So this is to us is very important and helped us solve the KT-TK co-critical graphs. So if you take a KT saturated graph, okay, now at least n vertices, KT saturated graph on at least t vertices. Either you can have a vertex adjacent to everybody, all the other vertices, or its minimum degree is high, at least 2t minus 4. And this boundary is that you cannot improve it. You cannot improve it. So for this one. Another one, since we only look for asymptotic bound. For asymptotic bound here, Nicholas Day here in 2017 had a nice result. So if you have a KT saturated graph with a minimum degree at least Q, then the number of edges is going to be Qn minus C. The C here is a constant. A constant means depends on Q only. It's independent of T, independent of N. So I hope you find this one amazing. It's independent of T. So this question actually was asked by Bolabash. His proof is very nice. He applied a Q-neighbor bootstrap population here to KT saturated graph. So we can solve KT-TK co-critical graphs to prove the lower bound because we used his idea, but we don't, our graph, red graph may not be, we applied it to a graph which is not necessarily KT saturated. We used his idea, Q-neighbor bootstrap population method for this one. That one is quite involved, so I will not talk about our proof idea, how we did TK there. So now the strategy here is just for 2 colors, for KTH2 co-critical graph. Now we can prove the red graph has a minimum degree at most n minus 2. Now I can prove the lower bound for my red edges. All I need to show you here is to prove to you the max degree is at most n minus 2. Now, as I said, for this one, it's more challenging. We have to use the percolation method to find its, to find the number of edges. To say this is also true, our constant will depend on K. K is the number of colors, KTTK. K is the number of vertices on my tree, okay, on the tree. Now the constant Nicholas they had here, his constant only depends on, doesn't depend on T, only depends on Q, the minimum degree here. The minimum degree you are giving me, okay? So this is the idea we had borrowed from his. Now let me see here, how do I count blue edges? Now blue edges now, it turns out to be easier, much easier to count if my second graph here is a star. That's why we did a C4 star. We didn't try anything else. We did a C4 star because C4 structure is new to us, okay, to us. So what do we do here? Now, because my blue graph is K1, K3, so which means the max degree is at most K minus 1. Now we are looking at how many vertices can be of degree K minus 2 or smaller. So I define this one to be a set here I'm looking for, right? Now, the number of edges, blue edges here is by Hand-Shake lemma. You have this. So all you need to do is find a upper bound for the number of vertices of smaller degree. Now for H1 equals C4, you can prove here S must be a clique. If it's a clique, then it has to satisfy Ramsey property because it doesn't have a red C4, doesn't have a blue K1, K minus 1. So you just use the Ramsey number and you have it. You have your upper bound. So you find your blue edges. You find your lower bound for your blue edges. So that's the strategy here. Now, so for C4 saturated graphs, we are very happy we find a result due to Ullmann here. So the proof is very technical. Now we tried to give a simpler proof, but we failed. We weren't able to. So this was proved back in 1972. So I hope he's happy we find one application of his result. Now, so the minimum number of edges is at least 3n minus 5 divided by 2. And these are the case when n is even, what does the graph look like? You can attach triangles here on this. So you have a main triangle here, and this one must have a vertex of degree 1. This has 2. This would be of all the case. Now this structure is important to us because we need it to construct our sharpness, to show the sharpness here. Now for his, with his one, we can prove the minimum number of edges in C4 star co-critical graph. C4 star co-critical graph here. So let me how come you didn't, for this one here, and let me slightly show you here why this topic is more interesting here, in the sense this time we cannot construct a graph with a unique critical coloring. Okay, with a unique critical coloring. We actually construct one with 6 critical colorings, different critical colorings. So and now you need to have some technical lemma. So one thing you would like to know here, if I have an edge belongs to many triangles, how many triangles it must have, it can have if it doesn't have, if I don't have a blue star, right? If I don't have a blue star. So the number of common neighbors you can have is at most is this one. If they have at least 2k minus 2 common neighbors here, this edge belongs to 2k minus 2 triangles. Now you can force yourself here. Then this edge must be colored red. So this must be colored red. So this technical lemma here is important for you. Okay, so let me not go to details, just to show you the construction we had here. Now, for when k is odd, I only show you the case when k equals 7 here. Now, this one is indeed, this is you get a unique critical coloring. So this for n is odd, n is even. N is odd, n is even. You have this one. The red graph you see here is exactly the one you saw from Ullmann's construction. From Ullmann's construction. And this one means this vertex is red adjacent to all the vertices in my a regular graph. I pick a k-regular graph on these many vertices. So I can do it in this way. Now, once again, it's going to be how do you prove this coloring is unique? You first provide a critical coloring, then you have to prove it's unique. That's the unique way. Up to symmetry, you can color it. So this is a unique one. Now, if k is even here, we actually have we have 6 critical colorings. So we have 6 critical colorings. So I want to show you in detail here because it's not easy to say by just saying one word here from here. The only thing we can promise you here, this edge must be red. You start from here and you try to deduce the coloring of the remaining edges of the remaining ones. So this is the first 3. This is the next 3. To you, it may look the same. You have to, so the line, I cannot fit them in. I don't want to read you. This is the one I took from the paper. I cannot make one on each slide because it was drawn together there. So that's for the one, for 6, I have 6 here. For the, when k is even here, so these are for all, when k is even and n is even. So I forgot to change the title here. So this is, when n is even, k is even here. So this one, we have 3 different colorings. We have 3 different critical colorings up to symmetry. I have 3 of them. Now for the C4 P3 critical graph, now this becomes simpler. This becomes simple. You have a unique one. You have a unique one. This is how we constructed for the unique. Okay. Okay. So for this one, then I will. So yeah, I run out of. I'm good. So this is that's all for my talk. Did I forgot to run the last page. So the last page I forgot. Yeah. So it's just I end my talk here with our recent paper on C4 Stark critical graphs. Okay. Thank you all.
Thank you very much.
Thank you.
Let's, are there any questions? But I'll stop the recording first and then we can. Yes. So thank you, Zi-xia.